Okay, so first, anybody have any questions on homework problems or anything like that? Okay. So the main thing to remember for next week is there are no labs because of MEA. So all week, no labs. And there is a Wednesday class, but there's not this class next week. So no Thursday class meeting. I will put up one lecture video and an assignment next week. I'll put up one today and then one earlier next week. I'll put up the video for the Wednesday class meeting in case it helps you. You'll have notes and video to look at. Okay, so that's the logistics. And we got to do more quizzes and more weekly assignments. So those will be coming soon. We have to, because that's what the syllabus says. I have to do what the syllabus says. Why did I write that stupid syllabus? I know. Okay, so now we're getting into the next topic. We've been doing kinematics. One thing that will definitely appear on at least one more quiz, partly because a lot of people got it wrong on the first quiz, is what kinematics means. So remember, kinematics is just studying motion without thinking about the causes. You could think of that as like the stuff you could get off of a careful video of an object's motion. You can see how fast it's moving, how far it's going, and that kind of stuff, but you can't see anything about how hard objects are bumping into each other and that kind of stuff. So that's motion without the causes. The next topic is kinetics. And that combines the motion, studying the motion with the causes. And those causes are mass and force. So those are the new things that we're going to be looking at, mass and force. I wasn't there when they named kinematics and kinetics. I'm like, 200 years too young or whatever. But if I was there, I would say those words are too similar. That's unnecessarily confusing. But I wasn't there. So remember that the simpler one, the first one, is the one that your ma could do because it's so simple. And then the harder one is kinetics. No offense to your mom. I'm sure she's very nice. Okay, so the big equation that we're going to use in kinetics, and actually the most important equation in this whole class, okay, so it's the most important equation in physics 1. Is called Newton's second law. And I'm going to abbreviate it. We're going to use it all the time, so I'm going to give it this abbreviation, N2L. That's what I'm going to call it. Newton's second law. There's also a Newton's first law and a Newton's third law, and they're also useful in different ways, and we'll talk about them, but this is really the key to this whole class. And Newton's second law says F net, the vector F net, and after I write this equation, I'll tell you what all these mean, is equal to M times the A vector, and I'll give this a subscript COM. So that's not more variables, that's just a more detailed name for that A. F net is the sum of all the forces acting on the chosen object. M is the mass of the chosen object. And ACOM is the acceleration of the center of mass of the chosen object. Since we're still treating objects as particles, ooh, that's another thing that'll be on a quiz. What's a particle? Since we're still treating objects as particles as if they have no length dimensions, they only have mass, no length dimensions, and those, we assume that the location of the object is its center of mass. I'm not going to be writing center of mass all the time, but I just wrote it this one time here to be clear that that's what we're talking about, the object center of mass. Like if, like for example, if I do this, my hands are accelerating as I do that, but the acceleration of my hands is very different from the acceleration of my center of mass, okay? And so that law doesn't hold for the acceleration of my hands or my feet or anything, it just holds for the acceleration of my center of mass, okay? All right, so before we can use this equation, before we can use Newton's second law, we have to define force and mass. I guess I'll do mass first. So define mass and force. Okay, so we haven't seen those yet because we've been doing kinematics, but now we need to talk about what those are. Mass is the simpler of the two. And this is something that I think we all kind of grow up with a little bit of an unclear idea about mass. I think we tend to grow up just because of, really, I think the reason that we think of mass as our weight is because bathroom scales have kilograms on them or whatever, and so you just get confused right from the start about like, okay, that's measuring your mass. Well, it's sort of indirectly measuring your mass, but that's not really how it's doing it. Like a scale, what it's measuring is the force that gravity applies to you. And that's different from the mass. What the mass is a measure of an object's resistance to acceleration. So if an object is really easy to accelerate, it has a low mass. If it's very hard to accelerate, it has a high mass. Resistance to acceleration. Shoot, I was just about to say something. Okay, so let's think about an example that kind of gets this idea across. Okay, like let's say that we have a pickup truck going, 10 miles per hour. And let's think of two different cases. One case where it collides with a compact car going 10 miles per hour the other way. And then another example where it collides with a semi truck going 10 miles per hour. Okay, well, what acceleration is acceleration measures how quickly velocity is changing. Okay, so if something's velocity changes really fast, that's a high acceleration. If it changes really slowly, that's a low acceleration. In one of these examples, well, let's look at so in both cases, this pickup truck is the same, right? In one of these examples, the pickup truck is going to, after the collision, keep going the same direction it was going, just slower. And in one of these examples, the pickup truck is going to end up going the opposite direction it was going. Which case is which? So like if it runs into the compact car, is the pickup truck going to keep going in the same direction or in the reverse direction? And so that means that the car has a low mass because that car is going to go from 10 miles per hour to the left to say 2 miles per hour to the right or something, right? That's a big acceleration. That's a big change in velocity in a short time, okay? So that car has a low mass. In the other case, the semi-truck is going to go from 10 miles per hour to the left to, say, 8 miles per hour to the left, right? That's a very small acceleration. The velocity is not changing very much in that amount of time. So up here, the car has a large acceleration, car. The semi is going to have a small acceleration. And the difference between these is just the mass of those objects. Okay, it doesn't have anything to do with the weight. Although, if you weighed the truck and weighed the car, it would also be true that the truck has a larger weight. Okay, but that's not really what acceleration is. What acceleration is if you do something to two of these objects, one's going to accelerate more and one's going to accelerate less, and that's based on their masses. Okay. The SI units for mass are kilograms. You might think it would be grams because it doesn't have the prefix. It seems more natural kind of, but kilograms is the SI unit. And an important thing to notice about the mass is mass doesn't have direction. It's just a positive number. there's no, like, it doesn't make any sense to say, like, what's this object's mass in this direction or its mass in this direction. It just resists acceleration. Whatever acceleration something tries to apply to it, tries to make it do. What that means, since this is a positive number, look at Newton's second law. And on the right side of Newton's second law, you're multiplying the mass times the acceleration. Okay, what happens if you multiply a positive number to a vector? What happens to the direction of the vector? Yeah, the direction stays the same, only the magnitude changes. So since F net is equal to mass times acceleration, and mass is a positive number, the vectors F net and acceleration are always in the same direction, always. So if you're in, let's just imagine like outer space where there are no forces on things, way distant, it's not even possible, but imagine way distant outer space, way past where satellites are and stuff, way outside the solar system, but an object's out there and you apply a force to it in that direction, you give it a shove that direction, that's the direction the acceleration is going to be. Okay, and if because of this thing, that force is always the same direction as the acceleration. And on the other hand, if some unknown force is applied to an object and it's the only force applied to it and the object accelerates that way, it means that that force was that way. Okay, those always are in the same direction. So we're going to do I'm going to do some calculations with scales and stuff in a little bit, sort of talk about how scales work, how, what they're measuring, that kind of thing. But for astronauts, and astronauts aren't way out in space like I was imagining, they're like inside the solar system. They're not really weightless, but it seems weightless because they're in free fall. Because that's what orbit is like constant free fall. But anyways, they experience this feeling of weightlessness. You can't use a regular scale to measure changes in mass if you're experiencing weightlessness. The scale would say 0. And it's really important for astronauts to measure their changes in mass because apparently you can lose muscle and bone density really fast when you're in space. And so they need to measure this stuff really carefully. They can't use scales. And apparently the way they do it, I've never seen this thing, but I've heard that what they do is they get in this contraption that just like shakes them. And it knows what forces it's applying to them. And it's measuring the acceleration that they get from it. And that change in acceleration is how they measure the mass. That's the definition of mass. I picture it like those, those things in like 50s videos, like with the like belts, like it was a workout machine. Okay, that's mass. So now force. This one's a little more complicated. Mass was just a positive number. Force is a vector. And it's a vector that measures the direction and intensity of a push or a pull. The units of force well, they just come from Newton's second law. And so look at this equation. On the right side, you can see that, you know, like the definition of a force is a mass times an acceleration. So that means that the units of force are the units of mass times whatever the units of acceleration are. That's length per time squared. So you get these really ugly units for force of mass times length divided by time squared. In SI units, that means kilograms, meters per second squared. But force is something that we're going to use all the time. And so people have just given it its own name because this is so cumbersome to work with. And so this is called the Newton. 1 kilogram meter per second squared is a Newton. And it's abbreviated capital N. Sometimes it can be a little confusing to figure out what all the forces are acting on a body. That's something we're going to spend a lot of time on actually in the next couple of weeks. But one thing to keep in mind is in this class, there are only two like sort of groups of forces. And so if you've dealt with these two types of forces, then you know you've dealt with all the forces on an object. So in this class, there are only two types of forces. The first one is the weight. That's the force applied to an object by gravity. And the second one is contact forces. And that is just contact from outside bodies at the chosen body's boundary. So like right now, I'm sitting here like this. Like what forces are acting on me? There's a weight force. Like at first you look and you're like, I don't know, there could be a million things, but there's a weight force. And then besides the weight force, all you have to do is just sort of imagine going around the boundary of my body and looking for places where other stuff makes contact with the boundary. So there's a force at my feet, there's a force at the chair, and then whether or not you're taking, if there was a strong wind or something, you'd have to take into account the fact that air is, but like right now, that isn't doing really anything. So all there is the weight force pulling down the floor on my feet, the chair, and then you're done. Okay, so that's a that's a good thing to keep in mind as we go through this stuff. Okay, so now what we're going to do is we're going to figure out what the force is that gravity applies to an object. Okay. Okay, so this is an important question. What's the force applied to an object by gravity? And we can actually answer this question because we know something about what happens with objects in free fall, and we can use Newton's second law. So we'll use what we know about free fall and Newton's second law to answer this. Okay, so in the video that you saw of the big room where they evacuate the chamber and drop the feather in the bowling ball, what we saw is that no matter what size objects are, no matter what the masses of these objects are, they accelerate downwards at 9.81 meters per second squared if they're in free fall. Okay. And so we're going to use that fact to figure out what the force is that gravity applies to things. So calculation 1. Let's say that we have an object that has a mass of 2 kilograms. What's the weight? You know, what's the force that gravity applies? Well, Newton's second law says that the force, and I'm going to break it up into its components. It's a vector, is equal to the mass times the components of the acceleration. And, you know, by the meaning of multiplication of a number by a vector, we can rewrite this as two separate equations. Fx is equal to m times ax, and Fy is equal to m times ay. And I didn't say this before, but let's think of the y-axis as pointing up. You get to choose your coordinate system. That's what I'm going to use. Okay, so what do we know about the acceleration in free fall? We know that the magnitude is 9.81 meters per second squared. And what's the direction? Down. And so that's a negative y component. And so what these two equations give us is that Fx is equal to the mass of 2 kilograms times, what's the x component of acceleration? 0, yep. So there's no horizontal force. And now do the same thing for the y component of the force. 2 kilograms times negative 9.81 meters per second squared. And that gives negative 19.62 newtons. So if you put this back into a vector form, you get that the force is equal to 0, negative 19.62 newtons. Or you could think of it as a downward force with a magnitude of 19.62 newtons. Okay. So let's do one more calculation with numbers. So this time, let's say that we have a 30 kilogram mass in free fall. Newton's second law says the force is equal to 30 kilograms times 0, negative 9.81 meters per second squared. So the x component is 30 times 0, so 0. The y component is 30 times negative 30 times negative 9.81. And so you get 294.3 negative newtons. And so that force vector is 0, negative 294.3 newtons. Or you could interpret that as a magnitude of 294.3 newtons acting down. Okay. So we could do this for all these different values, or we could do it for a general mass of m. And what you see is that in general, the force acting on an object with mass m, this is the gravitational force, is mg pointing down where this constant g is 9.81 meters per second squared. Okay, yeah, sorry. Okay, going too fast. Is that far enough? Okay. Okay, so what we did is we used what we knew about acceleration of something in free fall, and we used the fact that in free fall, the only force on an object is gravity, and we combined those two things to calculate the force that gravity applies to something in free fall. Now, the next thing, I can't prove this. It turns out to be the case, you can measure it and whatever, but You just have to sort of take my word for it. Does it make sense to you that the way that the force gravity applies to things is the same no matter what that thing is doing? You're just going to have to trust me on that. But, you know, if you put a 2 kilogram object rested on a table or whatever, this is the same, that force that we calculated in free fall is the same force that gravity is going to apply to it sitting on a table or if it's rolling or whatever. No matter what motion something is going through, gravity is pulling on it with the same force. Okay. Yes.
In those calculations, is there ever a time where there will be a number for AX, or is it always going to be 0?
Well, there's never going to be a horizontal force from gravity. It could be non-zero if you chose a different coordinate system, and there will be a couple times where there's a reason for us to choose rotated coordinate systems, so then you will have to deal with that. Usually, though, we'll choose the y-axis pointing up, and so that'll be 0.
Okay.
But gravity only acts down, so yeah. Any other questions right now? Okay, so now that we figured this out, we're going to sort of piggyback on that and see how to use that with other forces. Because now we did this first and figured out what gravity does. Now we can use what we know about gravity in other calculations. So this is going to show sort of what a scale is measuring, you know, when you get on a scale. So what's the force applied to this man by the scale? So there's the scale on the floor. Here's the man. In January, he's going to start working out. And let's say that the mass is 80 kilograms. The man has a mass of 80 kilograms. See, I do it too. It's like he doesn't weigh 80 kilograms. Weight is a force, you know. Mass is different from a force, but it's hard to, our heads tend to equate those two things. Okay, well, the first thing we have to do is figure out all the forces acting on the man. There's gravity, so that's one. And now all you have to do is just go sort of around the boundary of the man and find out any places where the outside world makes contact with the boundary. And there's only one place. Where's that? Yeah. The scale, yeah. So the forces are, so I'm going to go to Newton's second law. And I'm going to use the same coordinate system again with the y-axis pointing up. Okay, so we have a force of 0, negative 80 times 9.81. This is the weight force. And then we have this unknown force that's applied by the scale. And that's equal to the mass of the man times his acceleration. He's just standing there, so what's his acceleration? 0, yep. So this is the acceleration at rest. And so now I'm going to break this up into two separate equations. The first one says 0 plus fx is equal to 80 times 0. So if you solve that for fx, you get fx is equal to 0. And the second one says negative 80 times 9.81 plus fy is equal to 80 times 0. 80 times 9.81, this is 784.8 plus fy is equal to 80 times 0. Solve for fy, and you get positive 784.8 newtons. So put those together, and the force you get that's applied to the man by the scale is 0 for x, 784.8 for y. And so what direction is this force that the scale's applying to the man? Up, that's right. Remember, you can think of that as coordinates of the head of a vector where the tail is at the origin. So that's just straight in the positive y direction. So this is the force applied to the man by the scale. Okay, well that scale is measuring a force, not a mass. But how can a scale, like how does the scale tell you what your mass is based on this? Well, the scale company assumes that you're using their scale on the surface of the Earth, which is almost always a reasonable assumption, and so they just divide by 9.81, and that's your mass, right? So it's assuming that it knows, since it's assuming it knows that you're in a certain setting, it assumes it knows a relationship between that force and the mass. What if this was what if you did this on the moon though, let's say? What's the acceleration of gravity on the moon? I think it's like a sixth of what it is here. Can someone divide 9.81 or 10 by 6? What's that? 5/3? Okay, I can do that. So, let's do another example. So now the man is on the moon. And uses the same scale. The acceleration vector on the moon is, we'll say, 1.67 meters per second squared down. Okay. Here's the man. He has a mass of 80 kilograms. Okay, so Newton's second law. So it's the same setup. There's a weight force applied by the gravity of the moon, and there's a force applied to the feet by the scale, and that's all. So Newton's second law says 0, negative 80 times the acceleration of gravity on the moon, which is 1.67, plus fx, fy, is equal to 80 times the person's still not accelerating, so the acceleration vector is still 0. So calculate fx from this, and you get fx is 0. Do the algebra to calculate fy, and you get fy is, can someone calculate 80 times 1.67? $133.6. And so that force vector is 0, 133.6. Or an upward force of 133.6. Okay, but that scale still has a mass reading on it. You know, like it still has numbers on it that tell you what your mass is. Well, those numbers come from the scale measuring the force and just dividing by 9.81. Okay, and so in this case, the scale divides the force that it measures by 9.81 and accurately tells us what his mass is. You know, in this case, it divides by 9.81 and falsely tells him that his mass is about 14 kilograms. Okay? So all the scale is measuring is the force. It's not measuring the mass. On the other hand, if you had that contraption that shakes someone to measure, you know, resistance to acceleration, on Earth and on the moon, that thing would measure the exact same forces and measure the exact same mass for the person. Okay. Okay. Here's a practical use for this. Okay. So say your football coach says you need to gain 50 pounds by Saturday. Okay. How many newtons is 50 pounds? I think that's like 200 newtons. That's a lot. Okay, 200 newtons. Okay, so how are you going to do this? You can't put on that much muscle by Saturday, okay, no matter how much you work out. So what you want to do is have your coach measure you on a scale while you're accelerating. Okay, you might have to like sort of trick him or whatever, but you got to get him onto like a really powerful elevator that's going to accelerate when he takes your measurement. So so get on an elevator that's accelerating upward. So Newton's second law, let me draw the picture again. I just like drawing this guy. He's not even sure he wants to play football. His mom made him play. Okay, he has a mass of 80 kilograms. That means that his weight is 784.8 newtons. But he wants to gain 200 newtons. So he wants to weigh 984.8 newtons. So Newton's second law says there's a weight force. That's the force. That's the force of gravity, and he can't do anything about that because it's not enough time. So that's going to be 0, negative 784.8 newtons, right? That's the force that gravity is applying to him. And then there's also the force applied to him by the scale. So I'll call that Fx and Fy. And then that's equal to the mass times the acceleration. I think we're going to need a pretty big acceleration. So let's say, let's see. I think let's try an upward acceleration of 3 meters per second squared. Okay. So this is the acceleration of the elevator. By the way, you have to time this right because most of the time that an elevator is going up or down, it has a constant velocity. But right at the start of the motion and right at the end of the motion, as the velocity is changing, there's that second or so where there's an acceleration, and that's where you need your coach to read the scale. Okay, so the first equation says Fx is equal to 0. That's not a surprise. The second equation says negative 784.8 plus Fy is equal to 80 times 3. And so solve for Fy, and you get 1024.8, I think. So the scale reads a force of 0, 1024.8, or an upward force of 1024.8. And so you get to go in the game, but you get mushed because you're really not that big. Any questions about how that works? And you know, that's really like, you probably have, I mean, you have the experience in an elevator, like when it starts to accelerate, you feel the acceleration, you know. If you were on a scale, elevators don't tend to accelerate that much, so you wouldn't see that big a blip, but you would see when you started accelerating upwards, you would see the weight go up. And then when it started to slow down, when it reached wherever it was going, the weight would go down below what your actual weight is, you know? And when you started to accelerate down, the weight would go down, that kind of thing. Anybody have any questions about that? All right, I think that's about all I'm going to do today. But let me tell you about what the next stuff is that we're going to talk about. This will be short. So the next thing we have to do, we were able to calculate these things using Newton's second law without knowing anything about those forces, right? We just said, okay, there's an unknown force vector, but we had enough information to calculate everything about it, okay? Usually you need to know something about the force that you're trying to calculate. So usually you need to know, let's say, the main thing that you usually need to know is the direction of the force you want to calculate. So what we're going to talk about is the direction of three kinds of forces that we're going to deal with. So three contact force types. And these are pulling forces. We're going to always think of these as forces applied by a rope or a cable. A pulling force is something where you could imagine replacing, like if you're pulling on something with your hand, you could replace your hand with a cable and apply the same force. So we'll just always think of these as cable forces. Pushing forces. That's what we had with the scale force in the last example. We had enough information to plug into Newton's second law that we didn't have to know anything about the direction of this force, but usually we will have to. We won't have that much information. And then the third one is friction forces. And so probably over the next 2 weeks, we're going to be just learning how to identify these different type of forces and what you know about the directions when they come up. Okay, any questions? All right, bye. Yeah, thank you.